This is part 2 of the series Right Triangles and Trigonometry, and we're continuing on with our examples of using the Pythagorean theorem. In this problem, we have a right triangle with one leg and the hypotenuse this time, and we're going to be looking for the other leg. So let's go ahead and set it up. 4 squared plus x squared, the sum of the squares of the legs, equals the square of the hypotenuse. So now we need to solve for x, and you'll notice that I'm not going to square these values just yet. So let's put down x squared equals, we're subtracting 4 squared from both sides, so that's 7 squared minus 4 squared. And then I have to undo this square here because I'm solving for x, so I'm going to take the square root of both sides. So the square root of x squared is x, and the square root of this side is 7 squared minus 4 squared. Now, as I've done in the past, I've suggested this for several reasons. Use the calculator for the tool it's designed for. Don't use it as a thought tool, use it as a calculation tool. I like to do all my work up front on paper and then have one calculation in the calculator if at all possible. This reduces the chance that I'm going to make a simple transcription error or do something silly, drop a sign or something of that nature. And it also streamlines the process. So I'm going to go ahead and pull up my calculator. I'm going to put this in my calculator. So I'm going to have the square root of 7 squared minus 4 squared, hit enter, and there's my value. So x is approximately equal to 5.7. This is the preferred method when you're asked to give an approximation of a side length. If you're asked to give an exact value, then you have no choice but to go ahead and find the value of the radicand, that is the value underneath the square root symbol, the radical, and simplify it. But if you're just looking for an approximation, it's best just to type it all in as one string into your calculator. As it turns out, this is the square root of 33, and 33 doesn't simplify any further, so this is the square root of 33. So that would be the exact value, and this would be the approximation. Let's go on to another example. In this next example, we have, again, the hypotenuse and a leg, and we're looking for the other leg. Just as we did before, let's see if this is a Pythagorean triple. So this doesn't appear to be a 3, 4, 5, because this is not a multiple of 5. It looks like 5, 12, 13. It looks like it could be a 5, 12, 13, because this is 12 times 2, and this is 13 times 2. So if it's a 5, 12, 13, then 5 times 2 would be 10. So x should be 10. And let's just verify, just for kicks and grins. So we have x squared plus 24 squared equals 26 squared. X squared equals 26 squared minus 24 squared. X equals the square root of 26 squared minus 24 squared. Let's grab our calculator, and we have the square root of 26 squared minus 24 squared, which gives us 10, and verified that is in fact the case. So now let's move on to another topic. This next topic is going to allow us to determine if some general triangle is either acute, right, or obtuse based on side lengths, as opposed to what we're used to basing that on angle measures. And the way we're going to do this is we're going to couple it with a new theorem, the Pythagorean inequalities theorem, with the Pythagorean theorem converse. Again, the Pythagorean theorem converse says that if the square of the longest side of a triangle equals the sum of the squares of the two shorter sides, then the triangle is right. Now, if you take a look at this right triangle, and just for a second, imagine that the hypotenuse becomes shorter. If the hypotenuse becomes shorter, this leg is going to be pulled down, which means this angle is going to get smaller. If this angle is no longer a right angle, then it becomes an acute angle, making all three of these angles acute, since both of these had to be acute in the first place. And so that means that if the square of the longest side is less than the sum of the squares of the two shorter sides, then the triangle is acute. On the opposite case, let's imagine that this hypotenuse gets longer. If this pushes out this way, then this leg is going to turn around that point, which means this angle is going to open up. And if this angle gets bigger than 90 degrees, that angle becomes an obtuse angle. So again, here the longest side squared was equal. If it gets longer, the longest side squared is going to be greater than the sum of the squares of the two shorter sides, making the triangle obtuse. So this is easy to remember because you know that less than means smaller, acute, smaller triangle angles, equal, right, and greater, bigger, obtuse. So that's the coupling of the Pythagorean inequalities theorem, which is this first one and this third one, with the Pythagorean theorem converse. So let's go ahead and see if we can use these things effectively. For our first problem, we seem to have a fairly interesting one. We have this strange looking square root of 193, odd number here, and two other sides. Now the first thing we have to do in order to apply the Pythagorean inequalities or the converse of the Pythagorean theorem is we got to figure out which one of these is the longest side. Well, since this is 12 and this is 193, you know that the square root, or 13 squared, 12 squared is 144. 13 squared is 169. So you know that this number, this side length, has to be bigger than 13. So we know that the square root of 193 is going to be bigger than both of these two. So that's the one we're going to put on the left-hand side. Remember, the left-hand side gets the biggest one. So on the left, we put the square root of 193 squared. And on the right, we put 7 squared and 12 squared. Now, we're going to work this out and see what symbol goes in here, if it's less than, equal, or greater than. Well, the square root of 193 squared is just 193. And then 7 squared is 49 plus 144, which turns out to be 193. So the symbol in between here is equal. So this is in fact a right triangle because the square of the longest side equals the sum of the squares of the two shorter sides. Let's move on to the next problem. Here we have another oddball number. Obviously that's not going to be part of a Pythagorean triple, but is it going to be the longest side? Well, 4 squared is 16, and 2 times 4 would be 8. So that's this side at least, and that's a little bigger than 8. So we know that this is going to be bigger than these two sides. You could verify by putting in your calculator, but we can see that this is the biggest side. So this one goes on our left. 2 square roots of 22 squared, and then 8 squared plus 5 squared on the right. Now squaring this, that becomes 4. The square root of 22 squared is 22. This is 64 and 25. So this becomes, so this is 88 and this is 89. So here, this value is less than this, so this triangle is acute. Alright, let's move on to a third example. Now here we can see this is not a 3, 4, 5 or a 5, 12, 13 or any multiples, so it's not a Pythagorean triple. So it looks like it's not going to be a right triangle, but clearly this is the longest side. So let's put that side on the left. That's 7 squared. And then we have 6 squared and 3 squared. 49 and 36 plus 9. This is 49 and 45. So this is greater. So this triangle is obtuse. All right, let's move on to the next topic. Now we're going to be dealing with what are known as special right triangles. And there are two special right triangles, the first of which is a 45, 45, 90 right triangle. As the name implies, the two acute angles are 45 degrees, and we have one right angle. That means that if we have two 45-degree angles, then these two angles are congruent. And by the base angle's converse, we know that the two legs are congruent. So a 45, 45, 90 right triangle is an isosceles right triangle. And that's an important topic. Now, the theorem says that in a 45, 45, 90 right triangle, the length of the hypotenuse is a leg multiplied by the square root of 2. So what we're talking about here, we take the length of a leg and we multiply it by the square root of 2. Looks like a really odd idea and an odd number, but there's a very logical explanation for it. So let's take a look at that. Now here we have a right triangle. We know that this is a 45, 45, 90 right triangle because each of the legs is labeled A. That means they're congruent. So this is A and this is A. We need to prove that the hypotenuse is a leg multiplied by the square root of 2. So what we're going to do is we're going to apply the Pythagorean theorem to this. And by the Pythagorean theorem, we know that the square of the hypotenuse equals the sum of the squares of the legs. A squared plus A squared is simply 2A squared. So C squared equals 2A squared. To solve for C, because that's what we're looking for, what is the length of the hypotenuse, C equals the square root of 2A squared. Knowing our properties of radicals, we know that this is the same as the square root of 2 times the square root of A squared. And we know that the square root of anything squared is itself. So this is A square roots of 2. And so there we've just proven the hypotenuse, C, is equal to the leg, A, times the square root of 2. So a fairly easy, straightforward proof. Now the key for this idea, and what you have to keep in mind, is that the side opposite the 45-degree angle is labeled A, side opposite the 45-degree angle is A, and the side opposite the 90-degree angle is going to be labeled A square roots of 2. This image is what you have to remember, because when we solve for 45, 45, 90 right triangles, we're going to need to make this association. So this is an important idea here. Let's move on to the second type of special right triangle.